Right now, in a hyper-sterile clean room somewhere in the Netherlands, there is a piece of hardware that is roughly the size of a double-decker bus.
Yeah, a very, very heavy bus.
Right. And inside it, industrial lasers are firing into a vacuum chamber, basically vaporizing microscopic droplets of molten tin.
Like 50,000 times a second.
Which is just wild. And they're doing this to create a type of light that, does not naturally exist anywhere on Earth.
No, it doesn't.
And the crazy part is, if this one specific monstrous machine just suddenly stopped working today, the technological progress of the entire modern world would simply stop with it.
It really is the starkest paradox in modern engineering, when you think about it.
Yeah.
We have reached a point where, in order to manufacture the absolute microscopic foundation of our digital lives, we are basically forced to build some of the most colossal, complex, and honestly violent physical machinery in human history.
Welcome to this deep dive. Today we are exploring that exact paradox because we want you, the listener, to really grasp what is happening behind the scenes of your digital life.
Exactly.
We're looking at a recent, incredibly detailed article from the MIT Technology Review, and they got this rare inside look at a groundbreaking semiconductor manufacturing machine.
And it is truly groundbreaking.
It is. And as we map out what this machine does, we're going to look at the cold, hard mechanics of how a single company managed to basically corner the physics required to build the future.
Yeah, they really did corner the market on physics here.
We are talking about the hardware dictating everything. From the millimeter scale neural engines in the smartphone sitting right there in your pocket to the massive, super power-hungry future of artificial intelligence and quantum computing.
The goal today is to bridge that gap, the gap between what sounds like absolute science fiction and the brutal physical realities of high-end manufacturing.
Right. Because we think of the cloud as just, as a cloud.
Yeah, but the digital cloud, for all its invisible convenience, is entirely anchored to the physical capabilities of what this one specific machine can etch onto a slice of silicon.
Which brings us to the company building this behemoth. They're called ASML.
Right, a Dutch company.
Yeah, and they sit at the absolute undisputed forefront of semiconductor technology. But before we get into the microscopic physics of what they're doing...
There is a whole other level of crazy.
It is. But we have to grasp the sheer contradictory physical scale of the machine itself first. The MIT Technology Review describes it as a colossal maze.
That's a good way to put it.
Because it's constructed from over 150 tons of precision-milled aluminum. You weren't just looking at a shiny metal box like a giant MacBook.
No, not at all.
You're looking at thousands of snaking tubes, dense bundles of colored cables, and these massive pressurized tanks.
The visual complexity of it is just overwhelming. But it's a direct reflection of the physical tolerances required.
Nothing is there just for decoration.
Exactly. You are looking at over 100,000 highly specialized components and about 2 kilometers of internal cabling.
2 kilometers of cables inside a single machine.
Inside one machine. And it's so massive that just moving a single unit to a chip manufacturer requires chartering 3 Boeing 747 transport planes.
Oh, wow.
Just to ship the modules, which are then, reassembled over the course of several months by teams of specialized engineers.
Okay, let's unpack this.
Yeah.
Because my brain is really struggling with the economic and physical reality of a single piece of equipment like this.
It's a lot to take in.
You have a machine that weighs as much as a commercial airliner, but it requires this, millimeter perfect calibration. It's like building a skyscraper where if a single steel beam is a millimeter off, the entire building collapses.
That's a very accurate analogy, actually.
And the article notes the price tag for one of these units is a staggering $400 million.
$400 million, yeah.
Wait, how does a company justify dropping $400 million on a single machine? What is the ROI on something that costs more than a private island? Couldn't a hardware manufacturer achieve the same output by, buying 10 slightly older machines for a fraction of the cost?
What's fascinating here is that the $400 million isn't just paying for the 150 tons of aluminum or the 2 kilometers of cabling.
Right.
The price tag reflects a monopoly on manipulating physics at this specific scale. You literally cannot achieve the same result with 10 older machines.
Not even if you ran them all at the same time.
Not even with 1,000 older machines. Older tech simply physically cannot draw lines this small, no matter how many of them you run in parallel.
I see.
So when a foundry buys this machine, they're paying for the culmination of decades of research, trial, and error.
Which the article called the Valley of Death, right?
Yes. A 20-year valley of death where ASML poured billions into R&D without even knowing if this technology was theoretically possible.
So they were just gambling billions of dollars.
Exactly. So the foundries are buying the exclusive, absolute baseline ability to remain relevant in the next generation of computing. If you don't have this machine,
You're just out.
you cannot manufacture cutting-edge silicon, period. You are out of the global technology race entirely.
So it's basically a binary outcome. You either pay the $400 million admission fee, or you accept that your foundry is entirely obsolete for the next decade of advanced computing.
That is the brutal economic reality of the semiconductor industry right now. The barrier to entry isn't just financial capital anymore.
It's access to the physics.
Exactly. It's access to this highly restricted, impossibly complex physics manipulation.
Which brings us to the actual physics happening inside this 150-ton metal behemoth.
Yes, the extreme ultraviolet lithography.
Right, EUV.
Yeah.
The MIT Technology Review highlights this man named Jos Benschop as the visionary driving force behind this contraption.
He and his team really championed this EUV process.
And the core mission of EUV, as I understand it, is to etch unimaginably tiny patterns onto silicon wafers. To help you visualize impossibly tiny, I'm picturing something like trying to draw a highly detailed, perfectly functional city map on the head of a pin.
Okay, yeah.
But you are forced to do it using invisible light. Is that close?
I love that. The pin analogy captures the sheer lack of physical space really well, but it completely misses the violent speed and the repetition of the process.
Okay, how so?
Well, you aren't just drawing that city map once. You have to print that microscopic map perfectly millions of times a day.
Oh, wow.
Without a single atom out of place. And you're doing it in an environment that is constantly vibrating, dealing with massive thermal fluctuations. And this is key, operating inside a total vacuum.
Okay, let's stop right there. Why a total vacuum?
Because extreme ultraviolet light, the EUV in the name, has a wavelength of 13.5 nanometers.
13.5 nanometers.
Right. To put that in perspective, the visible light we see every day, like from a light bulb, is between 400 and 700 nanometers.
Okay, so EUV is vastly smaller.
Vastly. Visible light is literally too thick, the physical waves are too wide to carve the microscopic canyons we need on modern chips.
Like trying to paint a microscopic fresco using a giant wet mop.
Exactly. You need a finer brush, so you have to move to the extreme ultraviolet spectrum.
Makes sense.
But the problem is, EUV light is absorbed by almost everything in the universe, including the oxygen and nitrogen in the air we breathe.
Wait, really? Air absorbs it?
Yes. If you fire an EUV beam in a normal room, it disappears instantly. It just stops. So the entire internal operation of this double-decker bus has to take place in a vacuum.
So Jos Benschop's team didn't just have to figure out how to use this light. They had to figure out how to artificially generate a light that gets absorbed by air and then control it inside a 150-ton vacuum chamber.
That was the challenge, yeah.
How are they even creating that light in the first place?
This is where the engineering gets almost absurd.
I'm ready.
Inside the vacuum chamber, the machine drops microscopic spheres of molten tin.
Tin. Like the metal.
Yes, liquid tin. And these tin droplets fall at a rate of 50,000 drops per second.
The 50,000 drops per second, that's a continuous stream.
Practically, yes. And as each individual droplet falls, a high-powered carbon dioxide laser fires a targeted pulse at it.
A laser is hitting a falling microscopic drop of tin 50,000 times a second.
Actually, it hits each drop twice.
You are kidding me. Twice.
Yes. The first laser pulse hits the tin just to flatten it into a microscopic pancake shape. That maximizes its surface area. Then, a microsecond later, a second, much more powerful laser pulse blast that flattened tin pancake, instantly vaporizing it into a plasma.
A plasma. How hot are we talking?
Oh, temperatures around 500,000 degrees.
500,000 degrees inside this machine.
Yes, and that burning plasma is what actually emits the extreme ultraviolet light.
That is mind-bending.
It really is. And that violently created flash of light is then collected and bounced through a series of mirrors to project the blueprint of the microchip onto the silicon.
But wait. If EUV light is absorbed by everything, wouldn't it just be absorbed by the glass lenses inside the machine?
It would.
I mean, you can't use a normal magnifying glass or a normal mirror to direct this light, right?
No, you cannot use glass lenses at all. The light would just stop dead in the glass.
So how do they bounce it?
ASML uses a series of incredibly precise mirrors crafted by the German optics company Zeiss.
Okay.
And these aren't normal mirrors. They are made of alternating layers of molybdenum and silicon. They are specifically designed to reflect the EUV light without absorbing it.
That sounds expensive.
Very. And the surface of these mirrors has to be the smoothest surface ever manufactured by humanity.
Smoothest ever manufactured.
Yes. The metric the engineers use is that if you were to take one of these mirrors and expand it to the size of the entire country of Germany.
Okay, size of Germany.
The highest bump or the deepest valley on that entire massive surface would be less than 1 millimeter.
That level of perfection is almost terrifying.
It's hard to wrap your head around.
I mean, you have an environment where lasers are vaporizing tin into 500,000 degree plasma 50,000 times a second.
Yeah.
Creating invisible light, bouncing it off, mirrors the size of Germany with millimeter perfection inside a vacuum chamber, all housed within a 150-ton aluminum frame that was flown in on 3 747s.
And if a single one of those elements is out of alignment by a fraction of a hair,
the whole thing breaks.
the silicon wafer is ruined, and the $400 million machine is effectively a giant paperweight.
Unbelievable.
That is why the price tag is what it is. You are paying for the orchestration of controlled chaos.
Here's where it gets really interesting, because the article specifically points to the demand for these chips being driven by the cutting edge of the software world.
Mainly artificial intelligence and quantum computing.
Right. But let me push back on the hardware requirements for a second.
Sure.
We know tech companies have virtually unlimited budgets.
Absolutely.
Why are the massive hyperscalers, the Googles, the Amazons, the Microsofts, so reliant on these specific EUV chips?
It's a good question.
Couldn't they just bypass this bottleneck by building data centers the size of Rhode Island and filling them with thousands of slightly older, cheaper, larger chips running in massive parallel arrays? Like, are we just making chips smaller because we can? Or is shrinking the transistor to the atomic level the absolute only path forward for AI?
If we connect this to the bigger picture, the barrier isn't just computing power.
What is it then?
The hard barriers are thermal management, latency, and grid-level energy constraints.
Heat and power.
Yes.
Yeah.
People tend to think of AI or large language models as just, code floating in the ether.
It's just software.
Right.
Mm-hmm.
But training a model like GPT-4 involves calculating billions of parameters trillions of times over. If you attempt to do that on older, larger chips, the electrical signals have to physically travel further distances across the silicon.
And longer physical travel means more electrical resistance, which means more heat.
Exactly, and massively more power consumption.
Quite.
If you try to build a data center large enough to train a next-generation LLM using older architecture, you don't just need a facility the size of a city.
You need the power grid of a city.
You need the electrical grid of a small country just to power the server racks.
That's insane.
And you need a specialized cooling infrastructure that borders on an industrial hydro plant just to keep the silicon from physically melting under the thermal load.
Because all those older chips are generating so much heat.
Exactly. Furthermore, spreading the computation across a massive geographic area like your Rhode Island example introduces latency.
The speed of light becomes an issue.
Yes. The microseconds it takes for data to travel from one end of a Rhode Island-sized data center to the other ruins the synchronized training runs.
The math gets out of sync.
The math requires the processing to be physically dense. It has to be close together.
So it's a massive physics bottleneck. The AI companies literally cannot pull enough raw wattage from the power grid to sustain their software ambitions, unless the hardware engineers at ASML figure out how to make the chips do 100 times more math using 100 times less power.
That's exactly it. The AI revolution is entirely tethered to the thermal and energy efficiency of the chips inside the servers.
Wow.
EUV lithography allows you to carve transistors so incredibly small, we are talking measurements in single-digit nanometers, that the data travels shorter distances, generates vastly less heat, and consumes a fraction of the electricity per calculation.
So ASML is essentially building the only physical architecture that allows the software industry to scale without catching fire or bankrupting the global power grid.
Yes, without them, AI hits a physical brick wall.
And I imagine the same physical constraints apply to the physical realities of quantum computing hardware as well.
Oh, absolutely.
Because we're dealing with systems that require near absolute zero temperatures and atomic level precision just to maintain a stable qubit, right?
Yeah, right. Quantum computing introduces a whole new paradigm of hardware challenges, but the foundational truth remains the same.
Which is?
The manipulation of information at the extreme frontiers of science requires the manipulation of matter at the absolute atomic scale.
Software is caged by hardware.
Precisely. The software can dream up whatever impossible calculations it wants, but it is ultimately caged by what the physical hardware can execute.
So what does this all mean? I
Well,
mean, we've talked about data centers the size of cities and the hyperscale economics of AI,
yeah,
but it is very easy to get lost in the macro-level wizardry of server racks and LLM training models.
it is.
For you, listening to this right now, how does a 150-ton machine sitting in a clean room in the Netherlands translate directly to a granular everyday experience?
That's the real question.
How does vaporized tin and extreme ultraviolet light manifest in the device sitting on the desk next to you right now?
We can trace it directly to the most localized experiences you have with your hardware every single day.
Like what? Give me an example.
Take a feature like unlocking your smartphone with facial recognition in the dark.
Case ID.
Yeah.
It happens in a fraction of a millisecond. You just look at the screen and it's open.
For that to happen, an infrared sensor maps thousands of invisible dots on your face.
Right.
A neural engine on your phone's processor then has to run millions of localized calculations instantly, comparing that topographic map against the encrypted data stored on the device.
And it does that without sending the data away.
Exactly. It is not sending that data to a server in the cloud. It is doing complex machine learning inference locally on the device itself.
Okay.
To do that instantly, without rapidly draining your battery or causing the phone to overheat in your hand, you need billions of transistors packed into a piece of silicon the size of a cracker.
And the only physical way to carve trenches tight enough to fit billions of transistors on a cracker is by using a 13.5 nanometer wavelength of light.
Which brings us right back to the machine.
Right back to ASML.
When you hold your phone, what stands out to you about the fact that it took a $400 million machine to make it work?
I mean, it's just wild. The seamlessness of your digital life, real-time language translation, local AI processing, high-fidelity computational photography, all of it relies on the phone sipping battery power instead of gulping it.
Yes, and that power efficiency is the direct physical result of the extreme ultraviolet lithography, carving those impossibly small pathways. These microchips are the silent, invisible engine of modern reality.
It really reframes the objects around you.
It should.
When you look at the smooth, minimalist design of a modern device, it hides the sheer industrial violence and extreme physics required to forge the silicon inside it.
It's the ultimate abstraction layer.
That's a great way to put it.
The consumer sees a sleek pane of glass, right? But the engineer sees 500,000 degree tin plasma, Zeiss mirrors, and atomic-level thermal management.
We have covered an immense amount of ground today.
We really have.
We started by mapping the logistics of a 150-ton maze of precision-milled aluminum, snaking tubes, and vacuum chambers that cost $400 million to build.
The heavy bus.
The heavy bus. And we explored how Joss Benchop and the ASML team harnessed extreme ultraviolet light by systematically vaporizing microscopic droplets of tin 50,000 times a second.
A controlled explosion, basically.
Right. And we saw how that violent and visible process is the single structural pillar holding up our rapidly accelerating future, providing the massive thermal and energy efficiencies required to keep the AI industry from hitting a hard physical wall.
This raises an important question, one that the semiconductor industry is quietly agonizing over right now as they look to the future.
Okay, what is
We just spent this entire time talking about the heroic engineering required to draw ever tinier lines on a piece of silicon.
Yeah.
But physics has absolute non-negotiable rules. Atoms have a specific finite size.
Right. A silicon atom is roughly 0.2 nanometers wide.
Exactly.
You can only cut the pie into so many slices before you are literally trying to slice individual atoms.
And we are rapidly approaching that cliff. When you are carving transistor gates that are only a few dozen atoms wide, you start running into quantum tunneling effects.
Quantum tunneling. Meaning what?
The electrons don't stay in their lanes anymore. They just phase through the physical barriers because the walls are too thin.
Oh, wow. The electricity just jumps across.
Basically, yes. So, if we are already building $400 million double-decker bus-sized machines just to reach this current level of extreme miniaturization.
What happens when we simply run out of physical space on the wafer?
Exactly. Are we nearing the absolute hard physical limits of what humans and machines can engineer out of silicon?
Are we staring at the death of Moore's law? Or is this current marvel just the prelude to a completely new kind of material science that abandons silicon altogether?
It's a massive unknown.
It is a fascinating space to watch because whatever happens next, it will define the limits of what our technology can achieve in the next century.
Without a doubt.
Thank you for joining us on this deep dive.
Keep exploring the engineering hidden inside the devices around you. Keep asking questions, and stay curious.